Welcome to the deep dive. Get ready to look at your pantry shelf maybe a little differently after this one.
Yeah.
Today we're doing a deep dive into something that seems, well, incredibly ordinary. The pressure dynamics inside, like a vacuum-sealed agricultural canned good.
Right. It's funny, isn't it? We see these cans all the time, take them totally for granted.
Mm-hmm.
But understanding what's actually happening inside them, that involves some, fundamental physics and some really useful math.
Absolutely. And our source material for this discussion today, it gets into the concept of differential pressure.
Ah, yes, that difference between the pressure inside the can and the pressure outside.
Exactly. And our mission really is to unpack how these powerful mathematical tools, specifically derivatives, are pretty essential for evaluating how this pressure changes over time or with temperature.
And this is, I think, particularly relevant for you listening if you happen to be exploring differentiation and integration in your math studies right now.
Good point.
We're going to show you a very direct, sort of tangible application of those concepts you're wrestling with.
Okay, so let's picture the can then.
Yeah.
When it's sealed under vacuum, the pressure inside is deliberately made lower than the atmospheric pressure outside, right?
Correct. That external pressure is pushing in.
And that pressure the differential pressure you mentioned, that's what holds the lid on tight, keeps the can's shape stable.
Precisely. But, and this is key, it's not always a static situation. That balance can change.
How so?
Well, think about environmental factors. Temperature fluctuations are a big one. Like moving a can from a cool warehouse to a, hot store shelf in the summer.
Okay, yeah.
Or even changes in altitude. If you drive a case of cans up into the mountains, the external pressure drops.
Ah, right.
And these things cause the gases trapped inside and the air outside to expand or contract. That changes the pressure difference.
Okay, so things are dynamic. They're changing. And the source material seems to stress that just knowing the pressure difference right now isn't quite enough to understand, say, the can's integrity.
Exactly.
We need to understand how it's changing. And this is where derivatives come into play. Is that the idea?
That's precisely it. I mean, what is a derivative? Fundamentally, it measures the instantaneous rate of change of something, a function.
Okay.
So if we can model the pressure inside the can, let's call it pin, or the pressure outside, pout, maybe as a function of time or temperature, well, the derivative of that function tells us exactly how quickly that pressure is going up or down at any specific moment.
Right. Okay, I see. And this is where it gets really practical from an application perspective, like for the people making or shipping these cans.
Oh, absolutely. For them, knowing the rate of pressure change can sometimes be even more critical than knowing the actual pressure value at that instant.
Really? How come?
Well, imagine a situation where the internal pressure is increasing.
Okay.
If it's rising really slowly, maybe it's fine. It's within design limits. But what if the rate of that pressure change is suddenly very high, meaning the derivative, mathematically speaking, is a large positive number?
Okay.
Even if the current pressure reading isn't at the failure point yet, that rapid rate is a huge red flag. It tells you the pressure is spiking fast.
I get it.
And that kind of rapid change is often the signal of an imminent problem. Maybe the seal is about to break, or the can itself might start to bulge significantly.
So it's like seeing the trend, not just the snapshot. Derivatives let engineers analyze the speed of that trend.
Exactly. They can model the pressure inside as a function, PT maybe, if they're looking at time.
Or PT for temperature.
Or PT for temperature, right. And then taking the derivative P prime of T, or dP dt, gives them that crucial rate of change with respect to time or temperature.
Okay.
And this lets them predict behavior. By understanding what influences that rate, like, the type of metal used for the can, the kind of seal, even what's inside the can, they can design cans that are robust enough to handle the expected changes. It elevates the process from just measuring pressure to actually predicting and preventing issues, all thanks to understanding the rate.
It's actually a pretty neat example, isn't it? How these sort of abstract rules you learn for finding derivatives in math class have this very concrete job to do in analyzing a physical system, even something as everyday as a tin can. Evaluating that pressure change dynamically, using calculus, it gives a rigorous way to manage forces that might otherwise seem, well, unpredictable.
And it's worth saying, that we're using the can as our example here, but this core idea, analyzing rates of change with derivatives, it's fundamental everywhere. Fluid dynamics, thermodynamics, economics, population growth. Countless fields rely on this.
Okay, so let's just quickly recap this deep dive then. We've basically seen how figuring out pressure changes in things like vacuum-sealed canned goods is a really practical, real-world use for derivatives.
hmm It connects that mathematical concept. You might be studying differentiation, which is all about how things change. It connects it directly to physical things happening to everyday objects all around us,
Hmm.
like pressure.
Which brings us to a final thought for you, the listener, something to maybe mull over. If derivatives help us understand the rate of pressure change in a can, what other situations in your daily life, maybe dynamic systems around you, could be better understood if you measured how things change, using calculus?
Yeah, when it changes over time or maybe changes based on some other factor, could you analyze with a derivative?
Something to think about.